Let's take a quick look at electrophilic aromatic substitution. Electrophilic aromatic substitution means that my aromatic ring serves as the nucleophile. And the electrophilic aromatic substitution part, that's the aromatic part, right? It's the nucleophile. The electrophilic part is I need an electrophile. And so in this case, I'm going to use NO2. So we had to generate the NO2 electrophile. That would maybe be a separate video. In this case, I'm going to use that for the same set of reactions here. Same electrophile, but let's compare these different reactions with different nucleophiles. So if my first nucleophile is just benzene itself, okay, then the way this reaction would work is the electrons on the benzene ring, remember these are pi electrons, they can be nucleophilic, they'll reach out and attack the electrophile that is the NO2 plus. And so the intermediate that we would get is, we had an H, so I have left off the H's at each of these positions, but they're there, okay? So I'm going to put them in this intermediate because I've added NO2 to one position. I had to take electrons away from one of those positions, right? Because I took a pair of electrons right here. And so that meant I have now a plus charge right here. Now, of course, there are resonance forms that accompany that plus charge. And so we can move electrons around. So I'll have this plus charge, still a proton, a hydrogen in that position, still in this position, So I'm not changing that those are there, I just haven't always written them in. And then I can move electrons again, and I'll get the electrophiles in the same place every time, right? And the hydrogens haven't moved, but the location of the plus charge has. Okay, so it has been found in 3 positions on the ring, and those 3 positions are alternating around the ring. Now that will hold true for the next time I have the nucleophile benzene ring attack the electrophile, but this time I have a methyl group added, and a methyl group acts as an increase in electrons through induction. And so now when I add my electrophile, I have a little bit faster reaction, faster than benzene, because the transition state that I have to go through doesn't have quite as high of energy. And the plus charge that can form can be at a tertiary carbon. Okay, now there's continuing places where I can put that plus charge, put a circle around it here, as I move my electrons around. So I moved those up there, these are still here, and this methyl group is still here. And one more position, of course. We'll put that right here, plus charge, H, NO2, and the CH3. So those are 3 resonance forms just like above, but notice that one of those resonance forms is a bit more stable because it's a tertiary position. Okay, and so the overall energy for these resonance forms is lower than the overall energy for the first set of resonance forms. Now let's look at our third case. Our third case is still adding the same benzene ring to the same electrophile, but this time we have some electrons that can be added in from our substituent. This is anisole, and so this is faster still. Okay, because these are actual resonance electrons that I can add in. And so if I were to push those in, let's reach this out and draw my first resonance form. I've got a double bond to oxygen, plus charge on the oxygen. My electrophile has been added, and my benzene continues with its double bonds. Now, I can also write some more resonance forms for that. I'll push those electrons out. That will give me a resonance form with a plus charge here. My H and my NO2, I can move those around. Put this here, H, NO2, OCH3. And then one more position. So we had to cram 4 electron or resonance forms into this structure or into this space, because there's actually one more for this particular nucleophile. So the last one would have a plus charge here. And yes, there's still an H at that position. So this set of resonance forms has an even lower energy, because here I have, I have a completely octet satisfied resonance form. So that adds a greater stability to this set of resonance forms, and that's why it's faster still than the previous 2 substituents that were present on the ring. So electrophilic aromatic substitution depends on what has modified our benzene ring. Now let's do another example. This is electrophilic aromatic substitution with a benzene ring and the same electrophile, but this time I've added a very electron withdrawing group, right? So there's no resonance coming in from this like I had from here. This one was resonance stabilized. But for this one, I only have inductive pull. Only inductive pull. Inductive pull. Okay, because this is nitrogen's more electronegative, oxygen's out here electronegative, and so it is serving to pull electron density away from the ring. But nevertheless, I believe that this reaction can take place and we'll get a set of resonance forms. So in each of these cases, of course, I've got ortho addition, right? Let's go with this one. And I'll have my H and my NO2. I'll have my plus charge here. This is my first resonance form, and this is a very unfortunate one, because this particular one, we put a plus charge nitrogen next to a plus charge carbon. Okay, so I'm going to put a bigger frowny face there, because 2 plus charges next to each other are really quite destabilizing. So very destabilizing. So back here at the beginning, each of these other reactions were going faster and faster. This one is going slower than benzene. Okay, slower. And this is why. We have a set of resonance forms, and I can again move my electrons around. Set of resonance forms that are, one of them is actually destabilizing. HNO2. And then one more here. These are better. These are, you know, just standard secondary carbocations on our ring. Totally fine. HNO2. So this set of resonance forms, contains a particularly destabilizing resonance form. And so that means that the pathway to add this electrophile is higher in energy. All right, so if we think to our benzene ring starting point, any of these nucleophiles, here's our energy starting point. I'm going to have to go, you know, up in energy and then down a little hill to get to my product. Okay, let's say that this is benzene. And then if I have the slower, I'm going to have to go higher in energy to get to that product of the nitro group on it. Okay, so I know because you're looking at that and saying, wait a minute, but they both, right? I have 2 nitro groups. In fact, on every one of these, I have a nitro group. I added that. It's true. So the question is, how is the starting material affecting the height of this line? And so if I do one more, maybe even 2 more, well, that was not a very good one. Let me just rewrite that one. So I have to go over an energy barrier and then over an energy barrier. So these 2 that are faster and faster still goes down here, right? It's the least amount of energy to get to that product. And then this one is faster because it's still less energy than benzene. So this particular set of energy diagrams is not very attractive, and we'll go back to the textbook ones because they're nicer drawn. But this illustrates the difference between those starting materials and the substituents attached to them.